Welcome to Adventures in Math. In today's adventure, we explore the mirror image of exponential growth, the natural logarithm. We encountered exponentiation in our last adventure, but we only defined it for integer values for a base b not equal to the number e. We'll see what it means for a function to look in the mirror to find its inverse, and use this, along with geometry, to finally extend the definition of exponentiation to all real values and bases. First, we look at an example to see what it means to take the mirror image of a function, or equivalently find its inverse. In this illustration, we can see the curve y equals x squared and the line y equals x. We can imagine taking a mirror image or reflecting the curve y equals x squared across the line y equals x. Another way to visualize this is as folding a piece of paper along the diagonal to get the reflection. In this example, when we reflect x squared, we get the square root of x, which has a positive and negative solution for each non-negative value of x. We can see this since the reflection goes above and below the x-axis simultaneously. We can rewrite y equals x squared as y equals f of x, and then f of x equals x squared, where, for example, f of 3 is equal to 3 squared, or 9. We call f a function of x. We'll explore functions in more depth later in our adventures. For now, we can think of functions as formulas or templates where we plug in a concrete value for the variable or parameter x. So what exactly is an inverse function? Earlier we saw that the reflection of a function across y equals x gives its inverse. Besides being a mirror image geometrically, what does it mean though? We can think of it as reversing the operation of the original function or extracting the parameter we plugged in. Let's stay with our specific example of f of x equals x squared to make this concrete. In the case of x squared, we saw that its reflection or inverse was plus or minus the square root of x. When inverting x squared, we have two possible answers. To make things unambiguous, we'll choose to work with only the positive values, defining f inverse as the positive square root of x, which we write as f to the negative 1 of x is equal to square root of x. To see what an inverse function does, let's apply f inverse to y equals x squared. We simply get back x since the positive square root undoes the action of x squared. Since we restricted f inverse to only return positive values, the relationship works both directions. If we apply f to f inverse of y, we get back y. Now that we've gotten a better look at what an inverse is, what is the inverse of e to the x? In this illustration, we reflect e to the x across the line y equals x. We call this reflection the natural logarithm and refer to it as log. And in turn, we refer to e to the x as exp. Depending on the context, other bases than e may be used, and we will often write the natural logarithm as the letters ln instead. We have encountered rates of change throughout our adventures. For example, the rate of change of position is speed or velocity. One important way to represent these rates of change is with tangent lines, or lines that touch the curve at a specific point. We can see the blue tangent line touch the curve for y equals x squared at x equals 1 with y equals 1 as well. The slope of the tangent line is exactly equal to the rate of change at the corresponding moment in time. The slope of the tangent line is the ratio of the vertical change to the horizontal change, often worded as rise over run. When we reflect the function across y equals x, the tangent line comes along as well, but the ratio of the slope gets flipped, becoming run over rise. We've come across an important concept referred to as the inverse function theorem, which allows us to write the rate of change of the inverse function in terms of the original function's rate of change. In other words, the rate of change of the inverse function at y is equal to the reciprocal of the rate of change of the original function at the corresponding value of x. Let's apply what we just found, the inverse function theorem, to find an explicit definition for log. First, let's apply the theorem to see that the rate of change of log of y is equal to 1 over the rate of change of e to the x. We know that e to the x is equal to all of its rates of change, and that x is equal to log of y, since y is equal to e to the x in this example and is its inverse. We end up with 1 over exp of log of y, which simplifies to just 1 over y. In this illustration, we see the curve 1 over t in blue. Starting at 1, we can find the point at which the area under the curve is equal to 1, which is exactly e.
We can repeat this process starting at e and find that the area is equal to 1 when we reach e squared, or 2 if we measure the start from 1. We can continue to break up the curve into segments of unit area, delimiting them with successive positive integer powers of e. We can see that this extends to real valued powers as well, with the area under the curve from 1 to e to the x being exactly equal to x. Now we've seen that integer powers of e naturally segment the rate of change of the natural logarithm into units. Is something special about the curve 1 over t? It turns out that 1 over t is the positive portion of a conic section called the rectangular hyperbola. Conic sections, or more visually slicing cones in different ways, produce a variety of familiar shapes: circles, ellipses, parabolas, and hyperbolas. Here we can see different hyperbolas as we sweep through the angle their asymptotes form until we reach the rectangular or equilateral case. It is interesting that for the symmetrical case of an ellipse, we find pi as a ratio, and here for the symmetrical case of a hyperbola, we find e as the measuring stick for unit area. One peculiar property of 1 over x is that if we take the curve 1 over x and rotate it about the horizontal axis to sweep out a volume, we'll end up with what looks like a musical instrument, or a trumpet, sometimes referred to as Gabriel's horn. This horn has infinite surface area, but finite volume, exactly equal to pi. That means that you could blow on the horn, but you could never construct the horn. Now we have a way to compute both e to the x and the natural logarithm, where e to the x we compute as an infinite sum that we found in our last adventure that works for any real value. And now we have found log to be the area under 1 over t. Finally, we can extend exponentiation to bases b other than e and for all real values of x. We can define b to the x as equal to exp of log of b times x. Another way to think about this is that we're simply scaling the natural exponential curve to match the base b that we're given. We can also define a corresponding logarithm for the base b, which we denote log b of x. And we can define this as an integral in the same way as the natural logarithm, but what we're doing is scaling the hyperbola by 1 over natural log of b. This leads to the famous change of base formula for logarithms, which allows us to compute the logarithm for any base b using the natural logarithm. So we can write this as log base b is equal to the natural logarithm of x divided by the natural logarithm of b. In today's adventure, we saw the area under the rectangular hyperbola 1 over x defines the natural logarithm, and that e is the corresponding base, with its powers breaking the curve into segments of equal area. We saw what inverse functions were and used them to extend exponentiation to the real numbers. If you enjoyed the video, don't forget to like and subscribe.